Hey guys, let's talk about conjugate acids and bases. So that's the next topic that we're going to be talking about. When we talk about conjugate acids and bases, we know that we start with either an acid or a base. What happens is that if I'm an acid, like HNO2, and I donate that proton to the base, in this case H2O, that's the example that you have here, then I become an NO2 minus. Now that NO2 minus technically has the ability to pick up a proton again. So it can act as a base because it can be a proton acceptor. And whether it does so or not has a lot to do with what kind of base it is, strong or weak. But it has that ability. So the acid donates its proton and becomes a conjugate base. The base, in this case the H2O, picks up the proton that was lost by HNO2 and becomes a conjugate acid, H3O+. Now that H3O+ can donate that H plus to something else or just to the water, and then it goes back to its base. So it's acting as a conjugate acid when it does so. Okay, it's important that we be able to note these things because these species in solution may be able to do additional chemistry. So that H3O+ can do other things. We need to be able to identify that and look at what they are. Okay, so that's what we're going to be talking about. First, we're going to identify the conjugate of some stuff that we have here. I have a list of things that I would want you to identify a conjugate for. So the first of these is HI. Now, there's an H on it. It has an anion, so I know that this is an acid. That means it's going to donate that H plus and leave us with an I minus. And so the conjugates are HI, which is the acid, and I minus, which is the conjugate base, the anion that is left behind when the H plus is donated. So this is listed as a conjugate base. And I usually call these CB. So CB for conjugate base, CA for conjugate acids. Bear with me just a second, I'm sorry. I apologize for that. So that's the conjugate there. Now, if we're looking at H+, we know that that's the acid portion of something that's around. So the H+ has been donated, it left behind an anion. Therefore, if we're going to look for its conjugate acid, because this is a base at this point because of what it can do, then we have to be able to figure out what might have been the anion that goes with it. I'm going to put this on water. So if I put it on water, then I'm going to have an H3O+. Okay, so donating that H plus to the H3O+. All right, so one of the other things that we could talk about is, sorry. I mean, what I was looking for here is that this is an H plus. That means that it came from something that was an HA, so some anion on it. So what I was looking for was HA. That's where it came from. Okay. H2PO4 minus. So H2PO4 minus comes from phosphoric acid. It's after we've lost one proton there. And we have the opportunity to lose another proton, and that becomes HPO4 2 minus. The other thing that could happen here is that H2PO4 minus can pick up a proton to become H3PO4. All right. In this case, we're acting as an acid. In this case, we're acting as a base. Since I can act as an acid or a base, I'm amphoteric. Okay. And that, of course, means that this is a conjugate base and this is a conjugate acid. Okay. But they're conjugates. They're related through a single proton. All right. We can talk about HClO4. It will lose that H plus to become ClO4 minus. We can talk about BeOH2. Now, this is not an acid, this is a base. When it comes apart, it donates that OH minus to solution, right? And that OH minus can pick up a proton from somewhere else, and that's why it's a basic compound. But it's what's left after we donate that OH is what I'm looking for in terms of the conjugate. Okay, so it's what's left after it does whatever it its action is. So that's going to be a Be2 plus, and I know it's a 2 plus because I have two OH minuses on it. So Be2 plus is what I'm looking for there. CaOH2. We're also looking for the metal there, Ca2 plus. Okay, so when we talk about bases, we're looking for the metal that, and it's almost always a metal that goes with it. When we're talking about acids, we're looking for the anion. Okay, so that's what we're talking about. When we talk about RbOH, it's going to lose the OH to become Rb plus, and that is a 1 plus. Then we have CH3NH2. Now, this is a base. I know it's a base because I have that nitrogen. It can pick up an extra proton. So that's how it acts as a base. When it does pick up that extra proton, it becomes CH3NH3 positive. Okay, so that's what it will become. When we talk about the next one, that C6H5NH plus, I see that ours already has an H and a plus on it. So we're looking at a conjugate acid of a base. So I want to know what's the base, C6H5N. So we take off that H plus, because if it's a conjugate acid, it needs to donate that proton to become the base again. Okay, so that's what we're talking about there. As far as the rest of these go, so that next set, I'm going to have you work on those, and I will put up the answers on D2L. So I will get answers on D2L or HCl through NH3. Okay? So let's take ourselves into the next part of this. When we do that, we're looking, again, conjugate acid-base pairs. If an acid, like HNO2, it's going to have a conjugate of NO2 minus. And the question becomes, is NO2 a good base or a weak base? Strong base or weak base? Well, HNO2, based on its K, I know that HNO2 is a strong acid. So if this is a strong acid, that means that this thing is a weak base. So if it's a strong acid, it's very favorable for it to give up that H+. It doesn't want it back. So if that's the case, then my NO2 minus is not going to have a lot of affinity for an H+, and therefore we're going to have an HNO2 and an NO2 minus. The strong acids are going to have weak bases. Weak acids will also have stronger bases. Okay, so they're opposites of each other. In an aqueous solution, H3O plus is the strongest acid that can exist. If I have a stronger acid than that, HNO2 is a stronger acid than that, then that proton comes off and goes to H3O plus. That's the strongest thing that can exist in water. OH minus is the strongest base that can exist in water. So anything else that's around that's a stronger base will donate everything such that it becomes just OH minus. Okay? So that's what we're talking about there. And we'll talk about that a little bit more later. Okay? Conjugates. So let's do a little more practice with these conjugates. So I've got these tables. I have a compound. I want to know what the conjugate is. And I want to know which one's stronger, based on the fact that they're sort of opposites of each other. So HCN. I know that HCN is an acid. I can donate that H to become a CN minus. And the question becomes, is HCN a good acid or a bad acid? Well, it's not listed in my list of strong acids, so it's a weak acid. Its conjugate base, therefore, is a better base than it is an acid. So my CN minus is the one that has the stronger ability. When we talk about NH2COH plus, this species has already picked up a proton, right? So this is the conjugate acid of a base. So its conjugate would lose that proton and become NH2CO. Okay. And of course, when it does that, the question becomes, is it easier to pick up that proton or to lose that proton? Okay. So which is the better species? And it's better for this thing to be without that proton. Okay, so that means that the proton, the thing with the proton, is actually the stronger of the two things. So the conjugate acid is stronger than that weak base. Okay. When we talk about C6H7O6 minus, I know that it has a negative charge. So if I add a proton back to that, I get HC6H7O6. And again, it doesn't matter where that proton goes. There are reasons that it might go in a particular place, but you aren't expected to know that. So that's the species that I'd be looking at. And the question becomes, does the anion have more ability to pull in that proton, or does the acid have more ability to give it away? It's a weak acid, so chances are that the C6H7O6 minus is the stronger one. So it will pull protons from other places, okay? So that's what we're looking at there, is what kind of species is it? Is HCN a good acid or a bad acid? And if it's a bad acid, then it's more able to go back to become HCN. If NH2COH plus comes from a weak base, which it does, then the more active species is, once we've added that proton to it, losing that proton again. Okay, so that's what we're talking about. Questions, comments, problems on any of that? Now I'm going to go ahead and talk about another thing here. This is the acid-base strength from the scale. Acids, and what you might see in your homework or on a test is this chart right here. Now, if you see this chart, it's probably not going to have the base strength increasing. The arrows that exist here are probably not going to be there. But this is the way that this always works, okay? And we talked about anything that's a stronger acid than H3O plus donates those protons and leaves H3O plus. Okay, so HCl, H2SO4, HNO3 completely dissociate to become H3O plus. All right? When we talk about the strong bases, O2 minuses, H minuses, CH3 minuses, and we'll react with those solutions to give us OH minus. Okay, so those are the strongest bases that can exist there. I expect that you can look at this and pick out the better acid. So if I were to ask you which is the better acid, HF or H2S? Well, HF is above H2S in this list. So HF is a better acid than H2S. If I were to ask you which is a better base, F minus or HS minus, I would get that HS minus is below the F minus. And so in that list, it's going to be the stronger base. Okay, so again, opposites. That's what we would expect. So I would expect you to be able to use this table to tell me which one was better, to rank things. So if I give you 4 of them, tell me which one is the strongest, the weakest, get it, and who's in between, that kind of stuff. So that's what we're looking for in terms of that kind of question. Okay? So practice. We have our table. I'm going to zoom out so we can see the whole thing. That's helpful. So which is a stronger acid, H3PO4 or H2S? Well, I see that H3PO4 is right here. So 2 down from H3O plus. I see that H2S is then 1, 2, 3, 4 down from that. The higher one is the H3PO4. So H3PO4 or H2S. H3PO4 is the better one because it's higher in the table. Okay. If we talk about NH4 plus or H2O, if I look at this, H2O is listed right here. So it's at that break. And we're talking about bases now. No, we're actually not. So H2O is here. So 4th one up is H2O. And then NH4 plus is 1, 2, 3 above that. So NH4 plus is a better acid than H2O. And again, that's because it's higher in the table. We can talk about HCl or H3O plus. Okay, realistically, it's HCl because it's higher in the table. But we know that thing is always going to come apart to give us H3O+. So I would accept either answer. Both of them are logical. But I was looking for the HCl because it's higher in the table. All right? When we talk about stronger bases, let's go over here. Stronger bases. We want to talk about OH- or NH3. So now I'm looking for OH-, and that's 4 up for the bottom. The NH3 is higher than that. Now remember, this is the opposite trend. So the one that's lower is the better base. So OH- is the better base because it's lower in the table. Okay. F- and HPO4 2-. We have our H2PO4- is 2 down from the H2O, that line right there. And F- is directly below it. So F- is the better base because it is lower down. It's that simple. When we talk about CH3COO- or HS-, I have to find those species. So that CH3COO- is down from H2O. So H2O, SO4 2-, H2PO4-, F-, and then CH3COO-. Okay. When we look for the HS, that's 2 down from that. So since HS is lower, it is the better base. Okay. That's how we practice with that. And that's what we're looking for. I expect you to be able to use that table without the arrow reminders. Okay. So remember, our acids are always on the left side, higher in the table is a better acid. Our bases are on the right side, lower in the table is a better base. Okay. Questions about that? All right. I'm going to talk about, give me 2 seconds. I'm just going to talk in general about H+. So I've been using H+ all over the place, and I've been using H3O+ all over the place. So we can talk about H+, and we can talk about H3O+. H+ is listed as a proton. H3O+ is a hydronium ion. So I have a proton attached to a water. That's a hydronium ion. Now, does H+ actually exist? No, it does not. Okay, it never exists on its own. It's always attached to H2O and always is therefore the hydronium ion H3O+. But we're lazy chemists. Now you know that there are equations that we can write. We're only interested in writing the parts of that thing that are involved. Okay, so a net ionic equation only includes the parts that are involved. All right. So the H+ would be a net ionic equation for that because we're not including the H2O because it's just holding on to that thing, okay? So that's not what we're talking about. What we're interested in is what that H+ is doing. So that's why we do it that way. Now, understand, those are exactly the same when we talk about things that are H+ or H3O+. It does not matter how we refer to those. They mean the same thing, okay? Now I'm going to stop here. I'm going to go ahead and stop sharing, and I'm going to cut out, and I will be back soon. Thanks, guys.